Math 287, Quest to College. I'm Joe Vasta, and we are covering 4.1 and 4.2 in this video. So let's do 4.1 first. 4.1 for a lot of you guys is going to be a review. Vectors in Rn. So let's talk about what a vector is. A vector is a quantity that has both direction and magnitude. So there's an example of a vector. We've done column vectors. So I can write it as a column vector. And then here's the part that's going to upset you is this right here. Vectors in this class are going to be written using parentheses instead of triangular brackets or trackets. Now, why are we doing this? Because in this class we are covering inner product, and inner product has the triangular brackets, and things are going to get confusing if we use the triangular brackets. So in your book they'll use parentheses, and this happens often in higher math where vectors look like ordered pairs. So let's take a look at what this vector looks like. And once again, for a lot of you, this is going to be a bit boring because you've seen this in an earlier physics class or a math class. That's what the vector looks like. 1, 2, you plot the point 1, 2, and that becomes the head of the vector. And the tail is then 0, 0. And so that's what the vector looks like. It has a direction, and the direction's that way, sort of northeast-ish, not exactly, but it's like that. And it has a magnitude, which means it's a length of that vector. Now here's the deal. When I first saw vectors, this really confused me. But that vector there that I just put up equals this vector there. That's the same vector. So that freaked me out that you can pick up this vector and place it anywhere as long as you don't change its direction. And those vectors are equal. Okay, so the notation we use, you have to get used to that. And we'll move on to things that we can do with vectors. We can add two vectors. And now it said Rn in the first slide. We are looking at R2, that's 2 dimensions. Rn is n dimensions. So how do you add two vectors? Well, if we had put this using the column vectors, you would see that it's just like matrices. You add them component-wise. So 1 plus 3 is 4, and 2 plus 1 is 3. Let's take a look at a picture in terms of adding two vectors. You have the vector 1, 2, which is this guy right here. Then you have the vector 3, 1, which is that guy. Now there's a few ways of adding them. Some teachers like to say, well, put one of the vectors' heads on the other vector's tails, and that does work, but we're going to do it a little differently. This is also a popular way. You go ahead and you place, we are kind of doing that. We're placing this vector here, and we're drawing a parallelogram, and we're placing this vector right here. So it makes a nice parallelogram. Well, when you add those two vectors, you draw that diagonal from the origin to the other corner. And that red vector, look, it's 4, 3. Okay, so some teachers don't like to draw the whole parallelogram. They just like to draw a triangle. We're going to look at the parallelogram. So that's how you add two vectors in R2. And R3 would be the same thing. You would just have 3 components. Let's go ahead and look at scalar multiplication of vectors. What happens when you go 2 times the vector 1, 2? So here's the vector 1, 2. Well, you just multiply each component by 2. So when you have that, you end up getting 2, 4. Well, what does that do to this vector? So watch carefully. It increases the size by 2, the magnitude by 2. And so now it's that one right there. So that's scalar multiplication of vectors. Let's take a look at some properties of vectors. Let U, V, and W be vectors in Rn. If it makes it easier, you can think R3. R and S are scalars. So here's closure under addition. If you take any two vectors in R2 and add them together, that new result will be in R2. So that means it's closed under addition. You cannot get out of R2 by adding two vectors in R2. It's also closed under scalar multiplication, where you would say like a scalar like R or 7 times a vector is still in R2. Commutative property of addition. Doesn't matter which order you add the two vectors in, you're going to get the same result. Associative property of addition, if you have three vectors to add, you can add the first two and then add the third one, or add the last two and then add the first one. You're going to get the same thing. Existence of a zero vector. Well, there is an existence of a zero vector, and that is the only vector that when we draw it in R2 is just a dot. And so U plus 0, 0 is U. Okay, and I'm assuming R2. Existence of additive inverses. So you have that vector 1, 2, its additive inverse is -1, -2. Unit property, 1 times any vector is that vector. Some of these properties you're looking at and you're saying these are stupid, but in the world of math, theoretical things can be a little bit more complicated, especially if you're looking at more general cases. Associative property of scalar multiplication, you can take a look at that in the distributive property over vector addition and the distributive property over scalar addition. So all your vector fields will have those 10 properties. Okay, so there it is. Your vectors in Rn have those properties. Okay, so now I have the vector 1, 2. So this is what physics teachers like to do. They like to write that as 1 times 1, 0 plus 2 times 0, 1. And 1, 0 and 0, 1, they're kind of special. They have names, I and j. So this is 1i plus 2j. So mathematicians like to write vectors like as ordered pairs or with triangular brackets. And physicists usually like the i's and j's. Those are your standard basis vectors. And we're going to learn what a basis is later on. So that actually has a more complicated meaning there. Okay, let's take a look at a theorem involving some vectors in R2. Let A and B be two vectors. Okay, it just says let. There's a comma there, I don't know. Okay, so let A equal that and B equal that. Probably that comma shouldn't be there. And we're going to build a matrix, a 2 by 2 matrix using these two vectors in R2 where we load up the columns with those vectors. The area of any parallelogram with sides determined by A and B actually happens to be the absolute value of the determinant of that matrix. So, I mean, it's not like we want to go, hey, let's find the area of a parallelogram. That sounds fun. But this is what's important. A and B are collinear if and only if the determinant is 0. Because if you'll have the area of that parallelogram being 0, it means it's a collapsed parallelogram, which means A and B lie on the same line. Let's look at a theorem for vectors in R3. Let A, B, and C, and there's that comma again, let, comma, so I don't know what that's all about. Okay. Well, anyway, we're just going to keep going. You load up the columns with the vectors. There's the first vector, there's the second vector, there's the third vector. The volume of a parallelepiped determined by A, B, and C is the absolute value of the determinant. Now, a parallelepiped is when you put all these guys' tails together and you end up, maybe two of them make a parallelogram, and you draw that parallelogram, and then you add the third one, which kind of goes off of the plane of that parallelogram, usually. And it's like a box that doesn't have nice 90-degree angles. In fact, if these were all 90-degree angles, a special kind of parallelepiped is a box, but it doesn't have to be. Well, the volume of that parallelepiped is the absolute value of the determinant. And it's not like we're happy about finding volumes of parallelepipeds, but I think what we really need is this next theorem, which tells you that A, B, and C are coplanar. That means they all lie on the same plane if the determinant of A is 0, which means the volume of their parallelepiped happens to be 0. It's a collapsed parallelepiped. It's kind of, you can kind of compare it and contrast it to the theorem above. So those are some theorems that we'll see there. Now let's move on. Now we are in 4.2. 4.2 is called vector spaces. Let U, V, and W be vectors in V. Let R and S be scalars in F. So these look like the same conditions that we had for vectors in R2 or vectors in R3. But now this is going to be a lot more general. Your vectors U, V, and W might be matrices, polynomials, or even colors. So now this is going to become more general. Vectors are not necessarily arrows. R2, R3 are just some specific examples of vector spaces. So you've got these vectors, and you've got scalars. U plus V is in V, so closed under addition. R times U is in V, closed under scalar multiplication, and then you've got the commutative property and the associative property of addition. You've got the existence of a zero vector, existence of additive inverses, the unit property, associative property of scalar multiplication, distributive properties. Okay, if the preceding axioms, and that's what those 10 things are called, are satisfied for every U, V, and W in V, so for all the vectors, and every R and S in the scalar field will most of the time be the real numbers, then V is called a vector space over F. Okay, so now it's when things become very abstract. The worst part of chapter 4 is probably 4.2. followed by 4.3, and then it starts getting better. 4.4, 4.5, 4.6. Let's take a look at the next slide. Wait, it doesn't say suppose, does it? It says so a vector space is a container of 4 items. That's how I look at a vector space. Those 4 items happen to be vectors, scalars, vector addition, and scalar multiplication. There is no vector multiplication defined for just being a vector space. Okay, so a vector space is a container of these 4 items that satisfy the 10 axioms. A real vector space is a vector where your scalars equal the real numbers. A complex vector space is a vector space where your scalars equal complex numbers. Examples of common vector spaces are R3, or we could have put R7 or R2, any Rn, 3 by 2 matrices. That's an example of a common vector space. So the set of all 3x2 matrices satisfies those 10 axioms. And how do they satisfy the 10 axioms? Well, you can run down each of the conditions. If you take two 3x2 matrices and add them together, is it still a 3x2 matrix? And the answer is yes. So axiom 1 is satisfied. It's closed under vector addition. If you take a scalar and multiply it by a 3x2 matrix, do you still get a 3x2 matrix? And the answer is yes. So axiom 2 is satisfied. The vector space is closed under scalar multiplication. You can go through the list of the 10 axioms. You know, the next one would be if you have a 3x2 matrix and add it to another one, and then decided to do the addition in the different way and put the one that was on the left on the right. Does that make a difference when you're adding two 3x2 matrices? No, it doesn't. So commutative property of addition holds. All 10 axioms hold for 3x2 matrices. We could have picked any size of matrices. Well, in fact, over here, 2x2 matrices. The set of all 2x2 matrices make up a vector space. So it's hard to probably get used to the fact that I can point to a 2x2 matrix and say that that is a vector. P3R. What is that? Oh, I got to get back to this. This little r here means that the entries of your matrix, the elements of your matrix, are real numbers. And same with this. M2R means the elements of the 2x2 matrix are real numbers. So what's P3R? It says the set of all polynomials of degree less than or equal to 3 with real coefficients. That's what the R stands for. So the coefficients have to be real numbers. And so that's a common vector space as well, and we'll work with that vector space a lot in this class. C2, ordered pairs of complex numbers. We won't work too much with that in this class. Those are examples of common vector spaces. When we don't specify it, the scalars will be real numbers. And when we don't specify, plus is standard vector addition and multiply is standard scalar multiplication. So when we don't specify and describe in this container, the scalar is going to be reals and plus and multiply are going to be what you think they will be. But sometimes in section 4.2 they are weird, and we'll get to that. An example of a vector space we'll see later, so we don't want to stress out about this, is C3, 0 to infinity. And what is that? Those are real valued functions that are continuous and have at least 3 continuous derivatives on the interval 0 to infinity. So those vector spaces we'll see later on. We'll be examining those when we solve differential equations. Okay, so let's play this game. Is it a vector space? Now, before we play the game, is it a vector space? Let me just tell you something about your homework. We will be skipping homework. I don't want you doing the homework from 4.1 and 4.2. 4.1 is just because the homework problems are kind of dumb. You know, R3, R2. And 4.2, the homework problems are going to be like miniature proofs. And I didn't want to put you guys through that in this class. Now, having said that, you know, if you're a math major and you want to see kind of how I play this game, is it a vector space, then keep watching the video. Otherwise, the rest of this video is going to be me playing this game. I'll go back to some properties of vector spaces and show you something called the Three Stooges vector space. But in terms of anything else, if you're trying to do the bare minimum, then you can pretty much stop the video. Okay, is it a vector space? The set of vectors is Z. The scalars are the real numbers. Standard operations. Okay, now look what I have here. I have my list of axioms. this is, you'll probably be happy we're skipping the homework on this, but the homework in 4.2 that you do not have to do would be running through these 10 axioms, verifying whether they're all true or not. And that's what I'm going to do on some of these problems. So the first axiom says u plus v. So this is axiom 1. We're supposed to verify that u plus v is in the vector space. Okay, well, let's think about it. What kind of vectors do we have? Our vectors are integers. So is an integer plus an integer, is that in V? Is that another integer? And the answer is yes. There's no way you can add two integers together and get something that is not an integer. So axiom 1, you put a check mark. Axiom 2 says scalar times a vector is in the vector space. Now, what are your scalars? Your scalars are real numbers, so that's an F right there. So can you come up with an example of a scalar times a vector, vectors being integers, that end up not being a vector? The answer is yes, you can come up with many examples. I'll just come up with one. Your scalar can be any real number, I'll make it 1/2, and your vector is an integer, and I'll make that be 3. So here's your scalar, here's your vector, that's an integer. This equals what? 3/2, which is not an integer. Or in this example, I mean, that's what we're calling vectors. It's not a vector. So guess what? Axiom 1, or axiom 2, let's say axiom 2, fails. And so the answer to this, is it a vector space? The answer is no. This thing where your vectors are integers and your scalars are real numbers and you've got standard operations. That is not a vector space. Let's go ahead and do another problem. We're playing the game, is it a vector space? So the next one that I'm going to play is this one right here. So problem number 2. Your vectors, integers. Your scalars are integers with standard operations. So here's the deal. There are 10 axioms. Your vectors and your scalars are the same thing. So let's just run through these 10 axioms here. If you have an integer and you add it to another integer, so those are both vectors, is it in V? Is it also an integer? And the answer is yes. If I have a scalar times an integer, scalar, remember in our example, scalars are integers. So really this is just an integer times an integer. Is it an integer? Yes it is. Axiom 2 is satisfied. Okay. If I take two integers and add them this way, u plus v, does it equal v plus u? And the answer is yes, because when you add two integers, we have the commutative property of addition for integers. And if I have 3 integers and add them, and add the first 2 together and then add it to the third one, or add the last 2 together and add it to the first one, do I get the same thing? And the answer is yes. Is there an existence of a 0 vector? Yes, that would be the number 0. Is there an existence of additive inverses? Like if I have an integer like 7, what is its additive inverse? It is -7. You add them together, you get the 0 vector, which is just the integer 0. The unit property, 1 times any integer is just itself. The associative property of scalar multiplication, well, all 3 of these things are integers because we said the vectors are integers and the scalars are integers. And so that's going to work. You can verify that these will work. We end up getting, for this one, axioms 1 through Axiom 10, this is a pass. Those guys pass. Therefore, the answer is yes. It is a vector space. Okay, we're going to do 2 more. And this is, once again, for the math majors in this class. And maybe if you're an engineer, maybe you might go, oh yeah, this is pretty interesting. So this is going to be problem number 3. Your vector set of vectors happen to be R2, ordered pairs. Your scalars are the real numbers. To add 2 vectors in this world, we're going to go AB plus CD. This is going to equal A plus C, B plus D. So this is really standard vector addition. Scalar multiplication is going to be R times AB equals RA, comma, 0. This is not standard multiplication. This is not how we would multiply things in a standard R2 vector space. Look, R times AB is RA, comma, 0. So we're going to call this funky scalar multiplication, or we'll just call it funky multiplication. I'm going to do a lot more writing on this one than the last one. We're going to go ahead and verify the axioms. Axiom 1 is U plus V is V. Okay, so if you take 2 vectors, and the vectors are R2, they're ordered pairs, and you add them together, do you get another ordered pair? And the answer is yes. You can see it happening right here within the standard vector addition. So this one gets a check mark. Axiom 2. You take any scalar, which is a real number, times a vector in R2. Do you get a vector in R2 when you multiply? So when you do this, R times AB, does this thing happen to be in R2? Is it an ordered pair? And the answer is yes. Axiom 3. Now notice, what is different about this example? The thing that is really different is funky multiplication. So if any of these axioms are going to mess up, it's going to happen with something that has to do with multiplication. So, you know, like if you're looking at Axiom 3, is it commutative under vector addition? Yes, it is, because look at this. We just have standard vector addition. So we could verify it by writing out a formal proof, but we don't have to do that because these are true because addition is standard. So that would hold for 3, Axiom 4, Axiom 5, the existence of a 0 vector is 0, 0. And Axiom 6. Each element of R2 has an additive inverse that would give you 0, 0 when added together. So for these guys, Axiom 3, 4, 5, and 6, these are true since addition, or vector addition if you like, is standard. Okay, let's take a look at axiom number 7. Axiom number 7 says this. Okay, so we're looking at axiom 7. It says 1 times u equals u. Now, you might look at that and go, well, that should be true too, because 1 times anything should be itself. But let's look at the way funky multiplication. So this has multiplication, so we have to slow down. We're going to take an element from R2, which we'll call AB. And we're going to go 1 times that. So 1 times AB, I mean, you want to say AB, but you've got to follow this funky multiplication. And 1 times AB is actually going to be 1 times A, which is A, and then 0. It always has to be 0 there. So do we have 1 times AB equaling AB? And the answer is no. Axiom 7 fails. So that is very interesting, because now we know this game, you know how we're playing, is it a vector space? This right here is not a vector space. The first axiom to fail was axiom 7. Now, it's very interesting to look at the other axioms, like axiom 8 says this. Axiom 8 says RS times U equals R times S U. Well, if you are a math major, you know, this might be interesting to you. It might not even be interesting to you, but I'm going to see if axiom 8, 9, and 10 pass or fail. Once one of them fails, the thing is not a vector space. But I'm just going to go ahead and write out the proof here. So watch this. RS U would equal RS, let's call U AB like we've been doing, AB. So funky multiplication says, you know, RS is just some number. This is going to be RSA. And then RS times B, well, because of funky multiplication, you have to put a 0 there. So this right here is the left-hand side. Now the right-hand side, let's check that out. This is R times SU, which is R times S, and then U will make AB. So this is R. Now we're going to do funky multiplication, which would be SA, comma, 0. And then we're doing funky multiplication again with this R. It's going to be RSA and then 0, because that's what it says. And look what you have. You have the left-hand side equals the right-hand side. So A8 passes. Now it doesn't make a difference because this is not a vector space and we're just doing this for fun. And you might be asking yourself, why would you do this for fun? I guess you have a point there. I'm going to go ahead and fold this paper in half. It's just interesting to see what happens here. Okay, so let's look at A9. A9 says this. It says R, and then we have U plus V equals RU plus RV. Okay, let's look at the left-hand side. So the left-hand side says R, and then you know what I'll do? I'll write vector U as AB, and I'll write vector V as CD. Okay, so the left-hand side, let's see what it simplifies to. We have R times, vector addition is standard, so this is going to be A plus C and then B plus D. And then funky multiplication says I'm going to go R times this. So it's really going to be RA plus RC. And then you have to put a 0 in the second slot. Okay, once again, this is non-standard multiplication. Let's see if the right-hand side gives me the same thing. Right-hand side is R times U, which is AB, plus R times V, which is CD. Okay, funky multiplication both times. So this is going to be RA0 plus, and then this one is RC0. Well, I'm going to add those together using standard vector addition because we can. And this is going to be RA plus RC0. And look, the left-hand side equals the right-hand side. This would tell us that A9 passes. Let's take a look at our last axiom, A10. And this says R plus S times U equals RU plus SU. Okay, the left-hand side gives me R plus S, and then U will let it be AB like we've been doing. Funky multiplication says R plus S times A, which is really going to be RA plus SA, and then the last coordinate is 0, so that's funky multiplication. The right-hand side, we have RU, which is R times AB, and then plus SU, which is S times AB. I'm going to go ahead and do my funky multiplication, so I have RA0 plus, and then this one's going to be SA0. Okay, funky multiplication is done, and then I'm going to do standard vector addition, which gives me RA plus SA, and then 0 plus 0 is 0, which gives me the same thing. Left-hand side equals right-hand side. A10 passes. So, wow, this is not a vector space. So we've done a lot of work here, and I didn't even show the work on here because addition is standard. I'd be wasting my time, but it would look similar to this. But this is not a vector space, and we can note here that all axioms except A7 pass. Wow, so just one of the 10 axioms not passing can ruin a vector space. Let's go ahead and do our last one. Once again, I mean, I'm repetitive on purpose in terms of telling us do not do your homework. In 4.1 and 4.2, it will only damage you if you're a math major to do what you want to do. Let's go ahead and do the last one that we're going to ask for, which is number 4. And we're playing the game, is it a vector space? So your set of vectors happens to be R plus. Okay, so this is, you might want to be sitting down when you watch this, because this is going to be kind of weird. R plus, which happens to be positive real numbers. Okay, 0 is not included, by the way, because positive number is anything to the right of 0. Scalars are going to be real numbers. Okay, so we're not even going to put that. Remember when we said we don't write out what the scalars are, they're real numbers. Here's addition. X plus Y actually equals X times Y. I'd say that's pretty funky. And here is scalar multiplication. A scalar times one of your vectors, remember the vectors live in R plus, happens to be X to the R power. Okay, so this is so non-standard it almost hurts your brain. So I'll put this. This is non-standard. So let's see which axioms get broken. Here is Axiom 1, which says u plus v is in the vector space. Okay, so what do your vectors look like? They are positive real numbers. If you take one positive real number and add it to another positive real number, okay, you're not really adding them, are you? You are really, when you add them, so let's just say x plus y, okay, those are positive real numbers. When you add them, you get xy. Is the product of two positive real numbers a positive real number? And the answer is yes. xy is in the vector space. So A1 passes. Let's take a look at A2. A2 says this. It says R times U is in the vector space. Okay, so I'm going to take we'll go R, which is some real number, by the way, so your scalars are real numbers, and then a positive real number, we'll just call it x. Okay, and we see the rule up there, x to the r. So if you've got a positive real number raised to any real number, does that give you a positive real number? And you might say, no, it doesn't, but think about this. A positive real number would be like maybe 1/2, and you raise it to the -10 power. Is that a positive real number? And the answer is yes, because it then gives you 2 to the 10th, which is positive real number. Okay, so see if you can come up with an example where you have a positive real number, you raise it to a power and you get a negative number or you get 0. You can pause the video and think about it, but that's never going to happen. I mean, so you can go through this. So which means anytime you have r times x, which is really x to the r, that's our funky way of multiplying, this is in V. So A2 passes. A3. Okay, Axiom 3 says U plus V equals V plus U. Okay, so right hand side. No, let's do left hand side. Left hand side, U plus V. Let's just let U be like X, and then V is Y. Those are positive real numbers. And the right hand side says, oh, we're going to do this the other way, V plus U, which is really Y. Did I say plus? Whoops, I messed this up. U plus V is X plus Y. I didn't go the full way, so this is XY. Sorry about that. And then this is Y plus X, which is YX. So these are positive real numbers. For positive real numbers, is XY equal YX? And the answer is yes. Left hand side equals right hand side. A3 passes. Okay, let's continue this. A4. So let's just make this distinction here that this is positive real numbers, x plus y, those are vectors, equal xy, and r times x equals x raised to the r power. Okay, so that's the way we defined addition and scalar multiplication. Axiom 4. And once again, I mean, some of you are like, I should have turned off the video when he said. Well, maybe you should have, but I'm going to run through these axioms here. This one says U plus V, then we add it to W. This should equal U plus, and then we have V plus W. Okay, so the left-hand side, let's just make this be x plus y, and then this is plus z. So what does this equal? X plus y is xy, and then we have plus z. And by the way, that's a positive real number there. And then we're going to go ahead and do funky addition again, and this is going to give us xy times z, which is xyz. The right-hand side, this is going to get really weird by the time we hit axiom 5 and 6. Okay, so just know this is a little boring right here. This is x plus y plus z. So this is x plus, okay, what is y plus z? Well, funky addition says that you are going to be multiplying, so this is yz. And then we do funky addition again, which is xyz. Axiom 4 passes. Axiom 5. So this is where you probably thought it was going to break, and it might. It says a vector plus a zero vector equals that vector. So there's an existence of a zero vector. So you might be going, aha, Joe, your vectors don't even have 0. Okay, well, let's think about this. What could we do? We have x plus a zero vector. So let's just put a box there. We don't know what's going to go in that box. But remember, funky addition says that you've got to multiply. So this is x times whatever that is. And what we're trying to get, the zero vector says you have to end up with what you started with. So this has to be x. So this is going to be a part that makes some of you cry. Your zero vector, what number would you use where you go to x times that number equals x? It would be 1. So the zero vector equals the number 1. A5 passes. So if you look at your 10 axioms, it says there has to be an existence of a zero vector. It doesn't mean that it's always going to be the number 0. Now in this class, after this section, it most likely will be what you think it will be, but look at this. The zero vector in this thing, well, we don't know if it's a vector space yet, is the number 1. Axiom 6. If you've got any vector in that vector space, there exists an additive inverse, which gives you the zero vector. But what's the zero vector in our vector space? It's 1. So let's think about this. Is there something that you can add, and we'll do a different color for this, to any positive real number, and you end up getting the zero vector? So really this is funky addition, which means is there something that you can multiply, and it gives you the zero vector, which I'm just going to write as 1. So think about this. If you have a positive real number, what could you put right here that would work? Well, I'd say 1 over x. And it's not undefined. I mean, 0 is not in this set, and that works out. So 1 over x. Meaning this, if your vector is 3, some of you are going to really hate me for saying this, then your additive inverse, that means additive inverse is 1/3. Why? Because 3 plus 1/3 equals 1, the zero vector. A6 passes. We'll move on. A7. I think we can fit A7 right here. A7 says 1 times u is u. Okay, so 1 times x. let's think about what x is. X is a positive real number, and this right here is multiplication. Multiplication, so this is the scalar times a vector. Scalar times a vector is really that vector raised to the r, raised to the scalar. So 1 times x is x to the 1, and we know x to the 1 is just x, which gives us our exact vector. So 1 times our vector really is our vector, which means, and this is funky multiplication, this tells us that A7 passes. Aren't you glad that these are not going to be on your exam? Let's look at A8. A8. So for now, A1 through A7 passes. It looks like this thing could possibly be a vector space. A8 says RS times U equals R times SU. Okay, so here is the left-hand side. Left-hand side says RS, and then we'll let U be just X. Okay, so that's a positive real number, and these guys are real numbers. So what we have here is we have funky multiplication. So this is really going to be X raised to the RS power. Let's look at the right-hand side. So this says R, and then we have S times X. Let's just do that. Okay, so R is on the outside. S times X is going to be X raised to the S power. And now we're doing funky multiplication again, so this is going to be this guy right here, X to the S, raised to the R power. And you have a power to a power, so you multiply the powers and you have X to the SR or RS power. And so you have left-hand side equals right-hand side. A8 passes. A9 says this has to be true. Scalar times vector plus vector equals that scalar times the first vector plus scalar times the second vector. Okay, the left-hand side, okay, going a little crazy here. Okay, so what do we have? We have R, and then we have X plus Y. Okay, so let's take care of our X plus Y. It is XY, which happens to be a positive real number. That's a vector there. And then we're going to go ahead and do funky multiplication, which would say XY. We can put parentheses there if you want, to the R power. The right-hand side, so this is Rx plus Ry. That's really what we have there. And so I'm going to go ahead and do the funky multiplication. This is X to the R plus Y to the R. So you might think, aha, it's broken, but now this is funky addition. Funky addition says you multiply those together and you have X to the R, Y to the R, and we know properties of exponents. We can write this as XY to the R. A9 passes. Okay, A1 through A9 pass. A10, let's check this one out. R plus S times vector U, that should equal RU plus SU. Okay, so the left-hand side, I'm going to say R plus S times X. We're going to go ahead and do that multiplication. This is scalar addition here, so it's not funky addition. This is a scale plus a scalar, so we don't, that's, this funky multiplication is when you have a vector times a vector. So this is going to be, I'm going to have the scalar, which is R plus S times X. So this is going to be X raised to the R plus S power. Let's look at the right-hand side. Right-hand side is RX plus SX. Okay, so now this is funky scalar multiplication. This is going to give me X to the R. And then we have plus, because of the plus, and then we have S times X is x to the s. This right here, I'm adding two vectors with funky vector addition. So this is going to give me x to the r times x to the s. And because we have our rules of exponents, we can write it like x to the r plus s. Left-hand side equals right-hand side. A10 passes, which means what about this non-standard thing? This is a non-standard vector space. And the weird part about this, so the answer is yes, it is a vector space. The weird part about this is that the 0 vector, where this was, equals 1. And if you have a vector in the vector space being a positive real number, its additive inverse is its reciprocal. So vector spaces can be crazy. They're not going to be this crazy as we continue through linear algebra. This has got to be the weirdest section of the book. I'm going to go back to the PowerPoint. So we just did some examples. We're playing a game, is it a vector space? And so this sort of summarizes what I've been doing on the piece of paper. And once again, let me just remind you not to do homework in section 4.2. It will only hurt you when you go to do homework in the rest of chapter 4. I mean, you might be a math major and you might say, oh, I really like this stuff. I'm going to do some of the homework and verify the 10 axioms. You can do that if you want, but you've been warned. So let's finish up section 4.1 and 4.2 by showing you some additional properties of vector spaces. So you have a vector space. This is assuming you have a vector space now, and not one of those funky things that we showed you in the video. If you have a real vector space, the 0 vector is unique. Then 0 times u is the 0 vector, and s times 0 is the 0 vector. The additive inverse for each element in V is unique. Negative u equals negative 1 times u. And if s times u equals the 0 vector, s equals 0, or u equals the 0 vector. You don't have to memorize these properties. Vector spaces, once again, they're not just arrows. It's not just R2, though you have been working with vector spaces when you do work in R2 or R3. I'm going to show you a vector space that you might be weirded out by, and that would be the Three Stooges vector space. So here it is. I'm not going to go verify the 10 axioms on this, but I will kind of walk you through what I'm looking at here. The vectors are Mo, Curly, and Larry, and your scalars come from Z3. Z3 is mod 3 arithmetic, so like if you went 2 plus 1, that actually gives me 0. 2 plus 1 is 0. And 2 plus 2 is 1. So it's like clock arithmetic, and those are the 3 numbers on the clock. This happens a lot in abstract algebra at the university. So right now you might go, this is really weird, but it's so legitimate in higher math. So vector addition, I define it to be this way. Mo plus Mo is Mo, and Mo plus Curly is Curly. So Mo, Curly, and Larry are actual vectors. Vector addition is closed, and scalar multiplication is defined here. It's also closed. It will always give you a vector. The funny part about the Three Stooges vector space, it looks as if Mo is the 0 vector. And so you could actually run through the 10 axioms and verify that this is a vector space. There are the 4 containers that I was talking about. Here's your vectors. It's just a set of things. And in this case, it's the Three Stooges. Your scalars, this is a little funky, but it's Z3. The third part of the container is vector addition, and the fourth part is scalar multiplication, where your scalars come from this Z3. Let's finish off 4.1 and 4.2 by showing you some applications. We will see applications of vector spaces as we go. We have differential equations. You'll see that. Mathematical proofs, rotations, computer science. So if you're a computer science major, you'll get more out of the first half of this class. Fourier analysis, cryptography, coding, and the list goes on. Right now, it seems like you're in the clouds. It seems like this stuff is worthless. But once we finish this class, if you make it all the way to the end of this class with me, you'll realize that this class is just a foundational class to a lot more interesting things. So do not do the homework in 4.1 and 4.2. Have a good day. I'll see you in the next video.